All right, welcome back, everyone. So we are down to our last speaker for this summer school. So it's a pleasure to introduce Vedika Khemani from Stanford University, who will be talking about many-body physics and quantum error correction.
Okay. Yeah, thanks very much to the organizers for inviting me to talk about a topic I find very interesting. And thank you all for being here. So I'm, as a disclaimer, I am extremely jet-lagged and sleep-deprived, so please ask me lots of questions to keep me awake, okay? So the overarching theme of my talk will be the close relationship between the field of many-body physics, which studies the universal emergent properties, phases of matter, in systems of many, many interacting particles, and the field of information and computation, which is about the study of how data can be represented, manipulated, and protected against noise, which is ubiquitous in any physical setting. Okay. So traditionally, the field of condensed matter physics has focused on the study of materials in nature, which can organize themselves in a dazzling variety of different phases of matter, and the discovery and classification of these was a defining success of 20th century science. The big theme in my talk today, or the central message of my talk today, is that ordered phases of matter also furnish natural physical mechanisms for robustly encoding information, okay? Which is many-body physics, ordered phases gives you a way to correct, to build error-correcting codes which have a natural physical mechanism for noise protection built in. In this talk, while I'll give you various small examples of codes, to make this connection between many-body physics and information and computation, I'll always be thinking about families of codes defined in a scaling limit, where the number of physical qubits is being sent off to infinity, and we want to ask, how does the performance of this code change as the system size is increased? Okay, and this is important because phases of matter and the phase transitions between them are always only defined in the thermodynamic limit. Okay, so if I have a small code of 5 qubits or 7 qubits, that's very useful to gain intuition, and I'll certainly be talking about those, but you really can't think of those small codes from the perspective of a many-body physicist. Okay, so the types of codes that I'll talk about will be families of codes in this thermodynamic limit. Okay, so let's just do a couple of very familiar examples to illustrate how ordered phases of matter furnish this natural physical mechanism. Okay, perhaps the most familiar example, which we all know about, is a magnetic hard drive. Okay, and this magnetic hard drive stores classical information robustly. And the principle of how this magnetic hard drive works is that if we have a ferromagnetically ordered phase, in the symmetry, a ferromagnetically ordered phase, then this phase spontaneously breaks some kind of symmetry, for instance, an Ising spin-flip symmetry. And in this symmetry-broken phase, there are multiple degenerate ground states which have macroscopically different magnetizations, okay, which are related by the action of the symmetry. So in an Ising magnet, this would be the all-up and all-down states of the magnet. And now you can use this all-up and all-down states of the magnet to robustly encode classical information. In this case, all-up can be associated with the classical bit 1, and all-down could be associated with the classical bit 0. Okay? This is nothing but a physical implementation of the most simple code that you could possibly have, which is the repetition code. Okay? And now, in the presence of thermal fluctuations or noise, that we're always going to have a few spins that are going to flip and change their magnetization. But as long as a global collective magnetization is maintained in the system, then you're robustly storing either 1 or 0, okay, even in the presence of noise. Okay, so this is how symmetry breaking order, which is the most conventional kind of order you can think about, gives you a way to encode classical memory. Okay? However, as we know, protecting a quantum bit or a qubit is more intricate. Okay? You need to protect this quantum bit against not just bit flip errors, but also against phase errors. And the symmetry breaking magnet cannot do that for you, okay? Because in the symmetry breaking magnet, any stray magnetic field will dephase the all zero and all one states, and the phase coherence will be lost. So the magnet only protects you against bit flip errors, not against phase errors, okay? The other thing we know is that qubits cannot be copied. Okay, what the repetition code is doing is simply taking the classical bit, which is 0 or 1, and copying it many, many times in this global magnetization. But we cannot make copies of quantum bits. Okay, so we need a fundamentally different principle or paradigm to encode quantum bits. And Kitaev's breakthrough realization was that the different states of logical qubits can be encoded into highly entangled topological states, which are locally indistinguishable. Okay, these states are only distinguished by some global topological property and not by any local data. And this local indistinguishability endows these states with robustness against all kinds of noise. Okay, so in order to encode quantum qubits or quantum bits or qubits using some many-body physics principle, we need a different type of order, and we need topological order. Okay? So to summarize the two kind of paradigmatic classes of ordered phases of matter, which is spontaneous symmetry breaking and topological order, together can be used to encode classical memory and quantum memory. Okay? So incidentally, I heard there are many theorists in the room, so you may know that topological order is now also understood as a type of symmetry breaking, but of what are called higher form symmetries. Okay, so we have these okay, so that's just an aside, I don't need to get into that. Okay, so what these types of ordered phases gives you, if you think from the point of view of some Hamiltonian which is realizing this order, what this type of order gives you is a degenerate ground state manifold, okay, with many, many different states. I guess they don't have to be many, but with multiple different states. And these different states are related by the action of the symmetry operators. So for instance, in the Ising magnet, I can apply a global Ising spin flip symmetry to go from the all up state to the all down state, okay? So these are related by the action of these symmetries. And when these symmetries are macroscopic, these states themselves are also macroscopically distinct. Okay? So we want a degenerate symmetry broken ground state manifold, and we want these ground states to be macroscopically different from each other in order to encode information. Okay? In general, if we have 2 to the k ground states, this allows us to encode k logical qubits or bits into n physical bits, where n is my entire system size. Okay, so again, in the Ising magnet, I have 2 ground states, and that allows me to encode 1 bit. Okay, the magic of error correction comes from the threshold theorem, which tells you that you can have many, many, many crappy physical bits. Okay, they have some error rate p, and by making these states of many crappy physical bits, by putting in more and more, in the quantum case, by entangling more and more crappy physical bits, makes a better and better logical qubit whose noise rate scales down with increasing system size, as long as this code distance d diverges with increasing n. Okay, so that's the general kind of principle of what of how phases of matter kind of connect to error correction. Okay. Now, these two paradigms for thinking about phases, spontaneous symmetry breaking, topological order, this is extremely standard, and much of the work on trying to understand these types of phases of matter was inspired from the study of materials in nature, okay, which can organize themselves in these different phases. But the really exciting thing about our current moment is that we now have these incredible new experimental platforms across a wide variety of systems, ranging from neutral atoms to trapped ions to superconducting qubits, which we'll hear about a lot in the course of this conference. And these new experiments give us this unprecedented level of control over the interactions, the dynamics, and the geometry, even the geometry of the way in which these different entities interact with each other. Okay, so what this means is that we are no longer limited to thinking about phases of matter as they exist in equilibrium in nature, but rather we can think about very, very new settings for defining phases of matter, including out of equilibrium. Okay, again, what this quantum device is doing is giving you a controlled way to change the interactions between qubits in time and use that to manipulate information. Okay, this is fundamentally an out of equilibrium quantum process. So you can ask, are there dynamical phases of matter that we can talk about, and how might they help with not just encoding, but also processing and manipulating information? So this is a topic which I won't talk about much today, but it's a topic of a lot of current research interest. Okay? Perhaps even more strangely, you could ask, can I think about phases of matter in geometries that are different from the kind of local Euclidean space that we inhabit? Okay? In particular, when you're allowed to controllably change the interactions between these different entities, you can get them to arrange themselves in geometries of your choice. So I've given a few pictures of various non-Euclidean graphs that you could put these qubits in, and you can engineer these types of graphs either by using this kind of dynamical protocol as in neutral atoms, or by coupling to cavity modes, which is what that bottom figure is showing. Okay, there's many, many different ways of getting this kind of incredible control and this incredible tunability of dynamics and interactions and geometry. So this gives us this vast new frontier for many-body physics and error correction. And we can ask, what are new kinds of phases of matter and new kinds of error-correcting codes that's enabled by these new settings? Okay? So in this talk, I really won't mention dynamics at all, even though that's a topic that I spend a lot of time thinking about. Instead, I'm going to spend quite a bit of time talking about new families of error-correcting codes, which you've heard about a little bit in the prior lectures. These are so-called good quantum LDPC codes. So I'll unpack this in a lot more detail, but let me just give you some headline definitions here. Okay. So LDPC stands for low density parity check. This is a generalized kind of locality. Okay. So the usual codes that you're familiar with, the repetition code, the toric code, they also happen to be LDPC, okay? But the more general form of locality that LDPC codes allows is that given a particular graph, this could be a non-Euclidean graph, okay? Your interactions should be local on that graph, okay? So what that means is that if you define your code using certain checks or interaction terms, I'll talk about what these are, okay? Those should only act on finitely many bits or qubits, and in turn, each bit or qubit should only be involved in finitely many interactions, okay? So that's what LDPC means. And now, if you have codes which are local on certain non-Euclidean graphs, and you try to embed them into Euclidean space, you'll find that you're unable to do this unless you introduce very, very non-local interactions, okay? But again, we're not forced to live in Euclidean space when these new types of experiments can engineer geometries of our choice. So a natural question here is like, why do I care about engineering these geometries? What do these geometries buy us? And what they buy you is fantastic new types of codes which completely optimize or saturate bounds on this code rate k and the code distance d. Okay? In a good code, k and d can both be proportional to n. Okay? So k is how many logical qubits are you encoding? Okay? And the larger k is, the smaller your overhead is between logical and physical qubits, so that's great. And the optimal scaling you can get is k being proportional to n. And d is how different do your code words look. And the larger d is, the more robust your code is to errors. So k and d is, they're a measure of the robustness of your code and the overhead of logical to physical qubits in your code. And the optimal scaling is k and d both proportional to n. Okay? What's somewhat amazing is that these LDPC codes in the classical context have been around for many, many decades. They were actually discovered in the PhD thesis of Robert Gallagher in the 1960s, and then forgotten about for about 30 years, and then really became much more popular in the 1990s. And they're now used in all kinds of practical settings in telecommunications and so on. But it was this almost 40-year gap between the discovery of good classical LDPC codes and the discovery of good quantum LDPC codes, which were only formulated or only proven to exist in the last 2 or 3 years. Okay, so I'm going to be spending some time in this talk discussing how you can think about these new kinds of LDPC codes in the language of physics. Okay, much like we appreciate toric codes and repetition codes in the language of physics. Okay, and the very unique setting for these codes are that they have to live on these non-Euclidean expander graphs. There was a theorem proved by Bravi et al., I guess, in 2010, which said that as long as I'm thinking about these stabilizer codes, then if I'm in a local Euclidean geometry, then there are trade-offs between this code rate and code distance, which is how much information can I encode and how robustly I can encode it. And those trade-offs forbid these good codes from existing in local Euclidean dimensions. As an example, the 2D toric code, which I'll review for you, only has 2 logical qubits encoded, so k is 2. No matter how big you make n, you're not going to scale up the number of logical qubits. And the code distance d goes as square root of n, because in a toroidal or square geometry, the logical x and z operators only wrap around one linear dimension. Okay? And actually, this is not for lack of trying. You can prove that in 2D, the toric code saturates this bound by Bravi et al. On the trade-off between k and d. So you really cannot do better than the toric code in 2D from a scaling perspective. You might, you might be able to turn 2 into 4 by looking at some other 2D code, but fundamentally, you're not going to change the scaling that k is order 1 and d is square root of n. Okay? So I'm going to be spending a lot of time talking about these expander graphs.
Sorry, I just had a quick question.
Please.
So is this BPT bound on Euclidean, or you can also have like some kind of non-Euclidean graph, and then maybe this argument is going to be different for...
Exactly. So the BPT bound is for local Euclidean geometries.
Right.
So it does not rule out... maybe in the break, I can walk you through how the argument for the BPT bound goes. And that intrinsically cares about a surface to volume ratio. That's how it's derived. And that's how you get this trade-off in Euclidean space, which does not have to be obeyed in non-Euclidean geometries.
Okay, so then it's not in 2D. It's just like in Euclidean 2D, then you have this bound, but then non-Euclidean, you could stretch it a bit more. But
correct. In local Euclidean 2 dimensions, you have this bound. But if you think of something like a 2D hyperbolic tessellation, some kind of 2D hyperbolic manifold, then in fact you do get much bigger. Then this bound is not. It does not look like that. That's right. Good. So since I'll be talking quite a lot about these expander graphs, I just want to highlight, there's like there's math textbooks on expander graphs. You're going to do this very, very superficially. The main thing you should keep in mind about these graphs is that these are graphs in which the surface to volume ratio is proportional. Okay, so I can take this graph, I cut out any chunk of sites from this graph, anywhere, okay? And what I want is that the neighborhood set of that chunk of sites that I cut out is proportional to the actual bulk of the sites that I cut. Okay, so this is very different from 2D, where if I go in and I cut out a patch of sites somewhere here, then the boundary, the number of neighbors of that patch, is just going to scale like the boundary, which is parametrically smaller than the bulk. Okay, but in these non-Euclidean graphs, the boundary and bulk are proportional to each other. A good picture to have in mind for these types of graphs, they don't have to be locally tree-like. Okay? In fact, hyperbolic tessellations are a very common type of non-Euclidean graph that people think about. But one kind of very intuitive picture to keep in mind is a graph which is locally tree-like. So you have this branching ratio. You can imagine that you have, I just chose to pick a site which looks like the root. It branches, it branches, it branches. On a tree, it's very easy to show if you literally had a tree and you asked how many sites are there on the boundary of the tree. It's just, if the branching ratio is k and you've gone out r generations, it's just k to the r. And you can show that that's actually scales the same way as the number of sites in the bulk of the tree. Okay? However, it's not enough to just have a tree graph, because for this expander graph property, I need it so that no matter where I pick my chunk of sites, that boundary and bulk scalings are proportional to each other. Okay? So in order to do that, I need to deal with the leaves, okay? Because if I'm just looking at the leaves on an actual tree will not obey this boundary to bulk property. So then I need to close the tree graph up. So that's what those wispy lines at the boundary of that tree are supposed to denote. So this graph, if you pick any given point, it looks like a tree. But actually, every point is statistically the same as any other, so there's no designated root on this graph. Random regular graphs have this type of structure, and they're a very, very common kind of graph that's studied in this context. Okay, so the plan is that I'm just going to flesh out this kind of more conventional understanding between codes and Hamiltonians, which is how to think about classical codes as spontaneous symmetry breaking phases, how to think about quantum codes as topologically ordered phases. I'm going to flesh that out a little bit while staying in Euclidean space. And then I'm going to talk about much newer topics, which is going to get us to the forefront, which is all of our understanding of phases of matter is based on studying local models in Euclidean space. So how do we understand these good LDPC codes on expander graphs in physical terms? I'll present to you a kind of unified, what I'll call or what's called a homological description of quantum codes in terms of chain complexes. And I'll tell you how this helps us understand these models as generalized gauge theories and how we can formulate things like symmetry breaking order, topological order, dualities like Kramer's one-year dualities, which takes us between symmetry breaking and topological order on these graphs. And finally, I actually don't have this quote, but if you look at the abstracts of these papers which discovered these good codes, they're really math papers or like very abstract CS papers which take the form of theorems, proofs. And they use something called product constructions to construct these codes. But at least when I first looked at these papers, I didn't find much physical insight in them. And we spent quite a lot of time over the last few years trying to build up that physical insight. So I'll kind of share some of that with you and show you how you can think about these types of product constructions in terms of physics. For instance, using ideas like symmetries, redundancies, the nature of excitations, and so on. Okay, so that's the overall plan. Any questions before we dig in? Okay, so all right, so let's start with classical codes. And actually, one of the really amazing things that I didn't appreciate earlier, but have appreciated much more now, is that really by understanding classical codes, we can gain a lot of mileage in thinking about quantum codes, especially through these product constructions. So if you understand classical codes well, you're most of the way there. Okay. So for the classical, we're going to be talking about what are called linear codes. Okay, so these have some certain linear algebra structure, which I'll elaborate on in a moment. So for linear codes, again, our goal is to transmit k logical bits over some noisy channel. We do this by encoding it redundantly into some system of n physical bits, and n greater than k should be greater than k to have some redundancy. And n is often called the block length of the code, but I'll always call it the physical system size. Okay? So again, in the repetition code, if you want to transmit 1 bit of information, you can copy it into, for instance, n equals 6 bits. So you take 0 and you make it 0, 0, 0, 0, 0. 1 goes to all ones, and these all 0 and all 1 states are called code words. Okay? And now if you have some bit flips with probability epsilon, if it's independent bit flips, then it's probability epsilon to flip 1 bit, but it's probability epsilon squared, so much less to flip 2, epsilon cubed to flip 3. And now as long as the number of bits flipped is less than half the total system size, or less than d over 2, then the message bit can be recovered. Okay, and flipping more and more bits is less and less likely. Okay, so what's the algebraic structure of these classical codes? Okay, this is all going to be, the beauty is that it's all simple linear algebra over F2 variables, which are zeros and ones, and we can get extremely far by just doing this. Okay, so I have a system of n physical bits. Each bit can be in 2 states, 0 or 1. Configuration space is an n-dimensional vector space over the binary field F2. The binary field F2 just has 2 elements, 0 and 1. Addition is modulo 2. The identity is a 0 element. Bit configurations are vectors, are n-dimensional vectors. Okay, so they're like, if n is 6 and your vector looks like 1, 0, 1, 0, 0, 1, that denotes a configuration. You have 2 to the n configurations of this form. And you can view every configuration vector as, the configuration vector will have some number of ones, and you can associate those ones as picking out the subset of bits which are 1 in your configuration space. Okay, so it's very intuitive. And now to encode the code space, I want to pick a subspace of this full vector space. Okay, so because it's a subspace, the code space will itself form a vector space. So I'm going to pick out a subspace. I'm going to tell you how I pick that subspace out. But that subspace is going to have dimension k for my k logical bits. And because it has dimension k, you can think of it as having k basis vectors. So there will be 2 to the k configurations, which are my code words. Okay? Just like for physical space, there are n basis vectors. Every site can be identified as a basis vectors, and each of the 2 to the n, which gives us 2 to the n configurations. Okay. Any questions about this? I see a few confused faces. Yeah.
That you are choosing k sites, or
no, you don't have to choose. In a classical code, you can set it up as choosing k sites, but in general, and I'll talk about that. So you can think of your n bits, k of them are message bits, and n minus k of them are the kind of redundant encoding bits. You can set it up like that. But in general, when we move on to quantum codes, it's just going to be a subspace of the full Hilbert space. Yeah. Okay. Any other questions? Okay. So how do we select? Oh, sorry. Yeah.
Is there the orders of the bit in the subset? Doesn't matter.
does the order of the bit in the subsets matter?
Yeah.
You just have to pick an ordering. After that, it doesn't matter.
It doesn't matter?
No, as long as you're consistent with how you define it. People often put things in standard order where you can kind of rearrange your labels so that in a classical code, the first k bits can be your message bits, the rest are your data bits. But it doesn't matter. Like you just have to be consistent with what you pick. Yeah. Okay. So how do we specify code words? Okay. You can do this by imposing constraints on the allowed configurations, which are going to count as code words. Okay. These are often called parity checks. That's the PC in the LDPC. Why are they called parity checks? Okay. So in these linear codes that we'll talk about, all of the constraints are, this is like in what's called an XOR SAT satisfiability problem. Okay, so in classical computer science, there's a lot of literature on what are called satisfiability problems, which is given a set of bits and given a set of constraints, can you find solutions which satisfy all of those constraints? That's what these code words are going to be. In general, if your constraints are nonlinear, that's a very hard problem. It connects to the physics of spin glasses and so on. However, for linear codes, it's going to be what's called an XOR SAT problem. That's what this XOR, this symbol is. Okay, and this has a linear algebra structure which can be very efficiently solved. Okay, so suppose I have a constraint C1, which is x0 XOR x1. This just tells you that the combined parity of bit 0 and bit 1 should be even. Okay, so bit 0 and bit 1 together can be either 0, 0 or 1, 1, but 0, 1 and 1, 0 will violate that constraint. Okay, so in general, I'll have m such constraints, and the checks or the constraints themselves form a vector space over F2. Okay, so I can have, and these will have their own basis vectors. So for instance, if I have m checks, there's a m-dimensional basis which each of these checks. And the m-dimensional syndrome vectors, which are again vectors of ones and zeros, are going to denote subsets of selected checks. Okay, so for instance, if I have a syndrome vector which looks like 1, 0, 0, 0, 1, then that's telling me that I'm going to select check 1 and check 4, I guess, okay, or 5. All right, so this is telling me which checks I'm selecting. And then I'm going to specify my code using a parity check matrix, which is now an m by n matrix, which is a linear map between this n-dimensional vector space of bits and the m-dimensional vector space of checks. Okay? So every row, and I'll give you an example in just a second, every row of this parity check matrix tells you a check. Okay? It tells you here's a check. These are the bits that check acts on. And then if you act with this parity check matrix on some configuration x, okay, so x is an n-dimensional vector. If you act with the parity check matrix H on x, you get back an m-dimensional vector. That m-dimensional vector is the syndrome vector. The syndrome vector tells you which checks are violated in the configuration x. Okay, so that's more or less it. So because the code space has no violated checks, the code words have to satisfy that H acting on X gives me 0. Okay? So the 0 vector in this case is always a code word, because H acting on the 0 vector is obviously going to give you 0. Okay? And in general, the kernel of this parity check matrix furnishes a basis for all of your code words. Okay? So basically, someone hands you a parity check matrix. The parity check matrix specifies all the constraints in your problem. And the kernel of the parity check matrix gives you a basis of the code words. Okay? So K is n minus the rank of the parity check matrix. Okay? So this is simple linear algebra. Finding K and finding the basis for these code words is actually only polynomially hard. Okay? Now, once you have a basis of code words, you can start taking linear combinations of them modulo 2, okay, to get all the different code words. So that's how you go from k basis vectors to 2 to the k code word vectors. And if k is proportional to n, then enumerating all of those code words is an exponentially hard problem, but getting a basis for them is easy. Yeah?
Are there meaningful cases where the rank of age is less than the number of rows?
Yeah. And we'll talk a lot about cases where the rank of age is less than the number of rows. Those are cases where you have redundancies in your checks, linear dependencies, and that's actually extremely important when you come to constructing quantum codes. That's going to be one of the central kind of messages. I'll get to that. Yeah. Okay. Other questions? All right. And D is the minimum Hamming weight in terms of these. Hamming weight is how many ones are there in your vector. D is the minimum Hamming weight of a non-zero code word. While it's very efficient to find K, that's only polynomially hard. It's actually exponentially hard to find D because you need to actually list out all of the exponentially many code words when K is proportional to N to figure out what the minimum Hamming weight is. Okay, so here's a very, very simple example. Say I have 5 bits and 3 checks. Okay, so the first check could look something like x1 XOR x3 XOR x5. So then there's a 1 in 3 places in the first row, which tells you which are the bits that the first check acts on. The second row tells you which bits the second check acts on. The third row tells you which bits the third check acts on. This is often encoded in this graphical way. This is called a Tanner graph, where it's a bipartite graph. You put all your bits on one side, you put all your checks on the other side, and then you draw an edge between a bit and a check if that bit is involved in the check. Okay? So then this parity check matrix is nothing more than the adjacency matrix of this Tanner graph. Okay? Because you're just asking which bit and check have an edge between them. The LDPC condition can be framed in terms of this parity check matrix. So LDPC, remember, means that I'm now going to consider a family of codes where the number of bits is scaled up. So the number of columns in this matrix is going to get bigger and bigger. Appropriately, I should scale up the number of checks acting on these many bits. So the number of rows is going to get bigger and bigger. But as I scale up N and I scale up M, what I want is that the number of ones in each row remains finite, because that tells you how many bits each check acts on. And I also want the number of ones in any column to remain finite, because that tells you how many checks is any given bit part of. Okay, so the LDPC condition is nothing more than a condition that the parity check matrix is sparse. Okay, so it's natural to, in fact, we even just do this interchangeably. It's natural to associate these types of classical codes to classical spin Hamiltonians. I can go from n physical bits to n classical spins, which I'll sometimes call Zi for the Pauli sigma Z, and I'll sometimes call sigma I, corresponding to the values of 0 and 1. These spins can take values. I'm actually going to think of 1 as associated with 0 and -1 is associated with 1. It's not so important, but that's the convention. Okay, so you can have these classical spin variables. And now my M interaction terms, okay, which were this parity check interaction, is just going to look like a product of these spin variables. Okay, because you're just looking at the overall parity in this parity check, and that can be when your spins become pluses and minuses, that XOR sum becomes a product. Okay, so if I have a parity check matrix which has 1, 1, 1, 1 in these 4 rows in the first row there, that becomes a check which looks like sigma 1, sigma 2, sigma 4, sigma 5. Okay, so now using all of the different parity check matrix, you just add them all up with a ferromagnetic, uniform ferromagnetic coupling. This defines a Hamiltonian for you. It's a classical spin Hamiltonian. And the code words which satisfy all of the parity checks are the ground states of this Hamiltonian. Okay? So just like all 0 was always a code word, all up is always going to be a code word. But if you want k logical bits, then you need 2 to the k different ground states. And again, k is n minus rank H. So now here comes the symmetry breaking perspective, which I'll flesh out more in the next slide, okay, which is that these degenerate ground states can be associated with, again, I'm going to be thinking of some family where n is scaled up. It's going to be thinking of, you can think of these as the spontaneously broken states of some symmetry group, which is Z2 to the K. Okay? So your Hamiltonian is going to have a symmetry for every basis vector. Every basis vector of your code space is going to act like a symmetry in the Hamiltonian. And those symmetries are going to be spontaneously broken, which is what gives you the degenerate ground state manifold. Okay? So I'll give you an example in a moment. But this, and I'll also just mention here that this parity check matrix that I wrote down is a very is one that comes up quite often. It's the 743 Hamming code, where there's 7 bits and 4 logic. There's only 3 independent constraints, so 4 logical bits, and the code distance is 3 if you actually wrote it out. Okay, but let's talk about the spontaneous symmetry breaking aspect of this. Okay, so I have a class. Yeah. Mm-hmm. Yeah. Mm-hmm.
Could you explain to me again, how does parity check associate with the CA and interaction?
Yeah.
Could you explain one more time?
Oh, how is it associated?
Yeah.
Oh, it's just if my parity check matrix is 1, 1, 1, 1, like in the first row, in terms of bits, that looks like, so C1 in terms of bits is X1, XOR, X2, XOR, X4, XOR, X5. Okay, and then when I convert from bits to spins, this becomes an interaction terms, which is sigma 1, sigma 2, sigma 4, sigma 5. And when I add that to my Hamiltonian, what I need is that the number of minus ones between these 4 bits or spins is even. Okay? Yeah. Yeah. For the X operator, what do you mean by X operator?
X1 plus X1 XOR X2.
Oh, no. So these X's are these little X's. These little X's are bit variables. The bit variables, little x1, little x2, the bits are zeros and ones. Okay, so this is basically telling me that the number of ones between these 4 bits is even. Okay, so basically 1 in the bit language maps to -1 in the spin language, and 1 in the bit language with little x maps to 0 in the bit language with little x maps to +1. Okay, so every constraint in the bit language is counting how many +1s do I have? Is there an even number of them? In the spin language, it's counting how many spin downs do I have? Is there an even number of them?
Okay, yeah, thank you.
Yes. I can repeat your question. You can ask me.
Oh, okay.
Yeah.
I was going to ask, so sorry, this is for the recording.
Oh, okay.
So my question is the purpose of constructing the Hamiltonian just so you can like map the ground state to the code space, and then if you're not in the ground state, you can use like what state you're in to figure out like what error has occurred?
Exactly. So you know, the parity check matrix also tells you what the code space is and what, you know, the syndrome vectors will tell you which errors have occurred. So the purpose of mapping it to a Hamiltonian is to start thinking in more physical terms, right? Like I'll give you an example now on how to map the repetition code from the parity check language to the Ising model language. But once I map it to the Ising model language, I get a lot more intuition for what is the nature of excitations, what are the allowed phases, are they stable or not? So I can then build on the huge body of knowledge that, many body physicists developed in thinking about Hamiltonians in their phases.
Got it. Thank you.
Yeah. Yeah.
So the way you've written them right now, it seems like they are classical spin variables.
Yes.
Are you going to promote them to quantum spin variables?
I'm going to
as well?
promote them to quantum. So that's why I have that Z hanging out there. That's going to be my Pauli's spin Z matrix. So I can think of them as sigmas, or I can write all of these as diagonal Z Hamiltonians right now. Yep, good. Okay, so, oh, sorry, yeah?
Could you please explain why this K is n minus rank of H? I
Yes.
understand that the null space is
Yes.
the code space.
Yes.
But this, like,
Yeah.
logical bit.
Good. So each row of this parity check matrix is a constraint, okay? The rank of the parity check matrix is the number of independent constraints, okay? Because suppose I have a constraint in the first row and a constraint in the second row, and then I just take a sum of them modulo 2 and I add a third row to it, okay? That's not an independent constraint. If my first two are satisfied, the last one is automatically satisfied. So the rank is telling me the number of independent constraints, okay? And now, what's the code space, okay? If I have n bits and I have rank of H number of constraints, then you have to ask how many bits are left unspecified, and that's going to be my logical space. So K then is n minus rank of H. Okay? All right. Okay, so simplest classical code ever, the repetition code or Ising model. There's actually many different ways to, if I give you a code space which just has two code words, all up and all down, or all 0 and all 1, there's actually many different parity check matrices which could be compatible with that. Actually, we could have Ising models in any dimension as long as they act on 6 bits, which could be compatible with that. I've just written this in the for 1D, okay? So now you can see for the parity check matrix, each row, think of these bits now as arranged in a 1D line. So each row is looking at 2 nearby bits, okay? So I have bit 1 and 2, 2 and 3, 3 and 4, 4 and 5, 5 and 6, and then there's periodic boundary conditions in what I wrote, so 6 and 1. That last row, by the way, is not independent, okay? Because the product of all the checks here is the identity, okay, if I write it in spin language. So now, basically, you're saying that every neighboring pair of bits has to agree with each other. They need to be either 0, 0 or 1, 1. Okay, so you can go through that entire list. If I write it in a spin language, then it's nothing but the Ising model, sigma, sigma, for nearest neighbor Ising spins. In this case, n equals 6. Okay, there are 5 independent rows in that matrix, because that last row can be derived as a sum of all the previous rows before it. So rank of H is 5. So K is 1, which is my 2 logical bits. Okay, and the D here is n, because I have all 0 and all 1. All 1 flips every bit, so that's the minimum Hamming weight of something that's in the code space. And finally, this is the symmetry breaking perspective, where there's a Z2 symmetry group, okay? There's a logical X operator. So I have my trivial code word, which is the all zeros. Then the non-trivial code word that I get, which is the all ones here, if I think of 1, 1, 1, 1, 1, 1 as a symmetry operator, okay, this says every location where there's a 1, act with the Pauli X operator. So now I'm thinking about of this as a classical Hamiltonian with Pauli X and Z variables. And this code word defines this global spin flip operator, okay, which is product over all X. And you know that because all the checks, okay, are left invariant by this kind of flipping, okay, this is a symmetry of the Hamiltonian. So this is the good old Ising symmetry, which we're familiar with, and your two code states correspond to spontaneously breaking these two symmetry, this symmetry. Okay. More generally, what you would do is you have this code space, which has a basis given by the kernel of your parity check matrix. You can label all of your different basis vectors. So we're only going to look at the non-zero ones here. Okay. So I can look at all of my different basis vectors. That's what I'm calling my curly x. Each basis vector is just a vector with zeros and ones there. Okay. And now I'm going to say in the spin language, each of these basis vectors defines a spin flip operator. Okay. These are going to be my logical x operators. Okay. In my Ising model, if this was the logical 0 bit and this was the logical 1 bit, then to flip my logical bit, I need to flip everybody, okay, which means enacting a global symmetry operation in the language of many-body physics. Okay, so here I have many different logical bits. I have k logical bits, and each of them, each of them is associated with some vector of zeros and ones. That's a basis vector. That vector defines a logical x operator, which is act with the product of x's everywhere there's a 1 in your basis vector. These manifestly leave all the checks unchanged, so they're symmetries of the Hamiltonian. So now you have a symmetry group, which is not just Z2 like in the Ising model, but it's Z2 to the k. Okay? And in these good codes, k can be proportional to n, so this is actually a pretty large symmetry group. And all of these symmetries are going to be spontaneously broken. That's what it means for you to have the ground state manifold. Okay, and then someone was asking earlier about, can you always associate the logical, can you always think of the logical z's as one single bit? This is a little bit technical. It'll take 5 minutes for you to think about it, but I'm going to move on. But basically, if you have a logical x operator, you should also have a corresponding logical z operator, which tells you what the state of your logical bit is it 0 or 1? So for each x, you can actually associate a logical z. You can think of that as something that anti-commutes with this and picks out which logical state you're in. And for classical codes, there's some canonical basis choice in which each of these acts on a single site. So these are your k message bits. Okay? All right. So now I'm going to move on to quantum stabilizer codes, unless there are any other questions on classical codes. Okay, good. So quantumly, a lot of the same structure is going to continue. Okay, so now I'm going to have, again, some n sites. Each of these is going to host a qubit. So my physical spins live in some Hilbert space, which I've denoted here by curly h. Okay, so now instead of there just being identities in z's, we actually have Pauli matrices, which is identity x, y, and z, which acts on every site. These generate what's called the Pauli group. Okay, so you can take products of i's, x's, y's, and z's, and that gives you all 4 to the n possible operators that you can act on. So that's a Pauli group. The generalization of the parity checks, the XOR parity checks that I told you, are these commuting x and z stabilizers. Okay, so you can think of having two groups of checks. There's the x stabilizers and the z stabilizers, which are conventionally denoted by the letters A and B. The x stabilizers look like some products of Pauli x operators acting on some small number of sites. Likewise, the z stabilizers look like some product of Pauli z operators acting on some small number of sites. LDPC condition still holds. And these x and z checks are going to commute with each other. Together, these will generate what's called the stabilizer group. Okay, so if you take different products of x checks, you get the x stabilizer group. If you take different products of z checks, you get the z stabilizer group. together they give you the X and Z checks together will give you the stabilizer group. And now, much like the classical case, the code space is the +1 eigenspace of all the checks. Okay, so this is a quantum code. I have checks of both X and Z type. But because they mutually commute with each other, you can talk about the simultaneous eigenbasis of all of the checks. So your code space now is every vector that lives in Hilbert space, such that every operator that's in the stabilizer group, which is any operator which is the product of X and Z type checks, is going to be 1. Okay? So if I now think of a Hamiltonian defined by the checks, once again, I can just write the Hamiltonian as a sum over all X-type checks and a sum over all Z-type checks. Okay? And this Hamiltonian now has a ground state subspace, and that ground state subspace is the code space. Okay? So good. And you know, these stabilizer Hamiltonians play a very important role in physics. Previously, I told you about these Z-stabilizer Hamiltonians. They're classical. Here, I have a Hamiltonian made up of commuting stabilizer terms. These commuting stabilizer Hamiltonians, these have 0 correlation length, okay, because everything commutes with each other. And these often serve as fixed point Hamiltonians associated with some entire phase of matter. Okay, so I'll describe that. I'll probably take 5 extra minutes and just describe that for the toric code before we finish. Okay, so K again. Oh, sorry, that was for me. Okay, can we turn it back to the slide so I can see what I'm presenting from the timer? Okay, so K now again is the code space dimension. And it's given by the dimension of the K again is the number of logical qubits. Okay, and logical operators are those that commute with the checks but are independent and they're not generated by the checks. So you've already seen the toric code Hamiltonian multiple times. I'll go over it very quickly. Okay, this is the paradigmatic model for an error-correcting code. A quantum error-correcting code needs us to be in at least 2 dimensions. There are no 1D topologically ordered phases of matter. Okay, so for the toric code, you have a 2-dimensional lattice. Qubits live on edges. You have X-type stabilizers associated with vertices, which are these star terms, which look like the product of the Pauli X operators on the 4 qubits surrounding the site. And then you have Z-type stabilizers associated with plaquettes, which are the product of Z's on the 4 edges forming a plaquette. The toric code Hamiltonian is a sum of all X-type terms and all Z-type terms, which all commute with each other. And even though I'll draw this square, I have in mind a system with periodic boundaries here. Okay? The ground state, here I've drawn one of the ground states. I'll tell you about the others. This looks like what's called a loop soup in either the X basis or the Z basis. Okay? How do you see this? Well, suppose you start with the all-up state in the Z basis. Okay? If it's the all-up state, all the Z stabilizers are automatically happy. Okay? But the X stabilizers, it's not an eigenstate of the X stabilizers. To make it an eigenstate of the X stabilizers, we need to act with an X stabilizer. Okay? Acting with an X stabilizer creates a little loop on the dual lattice because it flips the value of the spins on the qubits on which the X operator acts. I guess you can't see my I'm not going to try to draw it, but you can see that if you act with an X on that star there, you create a little square on the dual lattice. Okay? To make it an eigenstate of that, you need to superpose the configuration where nothing was flipped with the configuration where that one little square was flipped. Okay? And then if you act with X on that superposition state, it's going to be an eigenstate of that X operator. Okay, now we need to do that for every X operator and every possible product of X operators, and that's what gives us this loop soup in the dual basis. Okay, and because the X and Z checks commute, by acting with the X operators, I don't mess up the eigenvalue of the Z operator. Okay, so this manifestly has both types of operators being conserved. And now, actually, I have a constraint associated with every site, a constraint associated with every plaquette. But actually, if I take a product of all X-type constraints on a system with periodic boundaries, then that multiplies to 1. So all except one of these constraints are independent. And likewise, if I take a product of all Z-type checks, I get something which multiplies to 1. So all except one of all the Z-type checks are independent. Okay? So this already, we'll talk about much more dramatic examples, but this gets to Sharon's question of like, why would I ever have my rank of H not be the size of H? Well, because I want, there are many cases where it's useful to think about translationally invariant systems. I could pick out one vertex or one plaquette and delete it from my list of checks, but that would kind of single out some one vertex, one plaquette as special, whereas you really want to think of this as a translationally invariant system with one constraint for the X and one constraint for the Z's. So because I have one qubit, one unspecified X constraint and one unspecified Z constraint, this allows me to get 2 logical qubits, which correspond to 4 different ground states on this torus. And crucially, all of these ground states are locally indistinguishable. They're identical locally. They look like eigenstates of these constraint operators, these local constraints, which are these X and Z type constraints. However, they're distinguished by some global winding number, okay, of these operators which look like some product of X's and Z's which wind around the non-trivial holes of the torus. Okay? So if you pick some non-contractible loop on the torus and you ask how many of these X's cut it or how many of these Z's cut it, that gives you this kind of topological information which distinguishes these different ground states, but locally they just look like loop soups. Okay, so if you look in a local patch of the system, you won't be able to tell which ground state you're in. So, so these different operators, which are my Z operators, which wind around the torus on the direct lattice, and these X operators, which wind around the torus on the dual lattice, okay, these label my different ground states. Okay, so I can start with a ground state which I call up-up, and by acting with one of these operators, I flip the state of a logical qubit, and I go to up-down, likewise down-up, likewise down-down. So you can see that all of these different ground states are macroscopically distinct. So they have code distance d being proportional to square root of n, which gives you protection against both X and Z type errors. They're locally indistinguishable, and because they're only distinguished by this global winding feature, this is a hallmark of topological order. In more modern language, these deformable X and Z type operators which commute with the Hamiltonian, okay, so these manifestly commute with the Hamiltonian, but they're not generated by acting with products of stabilizers. These form what are called one-form symmetries, and topological order is a one-form spontaneous symmetry breaking, where once again we have multiple ground states, but we can go from one ground state to another by acting with these symmetry operators. Yeah, question?
Could you please go back to the previous slide for a sec?
Yeah.
Okay, so on the next slide you said, these are the 4 logical qubits that
Yes.
we have.
2 logical qubits, 4 logical states, yeah.
4 states of 2 qubits. What are the second and third things you're adding on again?
Second and third, what do you mean?
Each ket is written as a
Oh.
superposition of these.
Yes,
different-
yes, yes. Okay, so if I multiply all the A's, I get identity. So I have one fewer vertex constraint, independent vertex constraint, and one fewer independent plaquette constraint than you would think. Okay.
Okay. Is this similar to the idea with stabilizer codes where you had the 6 rows, but one could be constructed as
Exactly,
linear
exactly,
combination? Okay.
exactly. So just think of AX as, or just think of BP, which is written in terms of Z's, as a classical stabilizer code, because it's purely acting on the Z terms. So you act with plaquette, 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 plaquette,
Yes.
okay, and then you multiply all of them, and you have one dependent row. Okay, So now I need an operator which will make up for that deficient constraint, and that's my logical operator. Okay? So the logical operator is going to basically, there's going to be two classes of logical operators, which are these guys here. Okay? So that's a product of z's over one of the non-contractible holes of the torus, and its conjugate x variable, which is a product of x's over the other non-contractible hole of the torus. Okay? And now you can see that I can't take any product of plaquettes to produce this kind of line operator. So it's independent. However, it commutes with the product of all stars, or it commutes with every star, and it commutes with every plaquette. All of these operators. And this x and the z, which wind around the different holes, you can see that they meet on that one site. So they're going to anti-commute with each other, which is what you want for associating this with a logical x and a logical z.
Okay.
Does that make sense? Because you have to have the right Pauli algebra.
Okay. So we're writing it as like a superposition of like the logical 2-qubit state plus like what you get when you act the logical
Exactly.
z plus what you get when you act the logical x, and these represent like logical errors. Is that what you're saying?
They represent different logical states, and indeed, if your error model produced these naturally, it would be a logical error. So basically, I'm saying in that first one, which is the up-up, I generate that up-up state, which I'm calling up-up, by I start with all zeros, and then I keep acting with these star terms, which creates a loop on the dual lattice. And then I act with all possible loops, and I get that first term. That first up state, okay, if you look at the evenness or oddness of how many red lines cut a non-contractible hole in the torus, that will always be even. You can see there. Okay, like even when I have those non-contractible ones, there's always an even number of them. Now I want to get the other logical state. The way I get the other logical state is to start with that up state. And well, I want to flip one of the spins. So I need to act with a logical x.
Oh, I see. Okay.
And acting with the logical x means acting with that non-contractible operator on the dual lattice. So then you can see every configuration that I had up there, I flipped one extra non-contractible loop relative to that.
I see. Okay.
And then down up is again acting with up, but on the acting with the logical x, but now on the other hole. So now you can see relative to the first one, I flip the state along this vertical line, and then down is acting with both.
Okay, so it's basically the idea that like if you want to go from up to up down like logical states, you would act a logical x on the second qubit, and so you would do that like non-contractible.
Exactly. And this is because I wrote the states in the z basis and I labeled it that way. I could have equivalently written everything in the x basis, and then to go between, then that would have been plus plus, plus minus, minus plus, minus minus, and then to go between those states, I would have acted with logical z operators, which act on the dual lattice and not the direct lattice.
Okay, thank you.
Yep. Okay. All right. Okay. So, okay, just 2 more minutes to get to the punchline. Okay. So a hallmark of topological order is deconfined excitations. Okay. So all of these, this topological order, you can think of these star type terms as being associated, violations of star terms. You can think of them as electric charges. And violations of plaquette terms, you can think of them as magnetic vortices. And now, if I act with some string operator, which does z like that on some ground state, I create 2 excitations at the endpoints of those strings. And I act with x operators on the dual lattice, I create m vortices on the endpoints of those strings in the plaquettes. Okay? So now the point is that the only things that cost energy in my Hamiltonian are the locations of those excitations. Okay? The strings are completely tensionless. Okay? So these charges can move around freely without any additional penalty as long as there are only two types of E charges, the energy cost is 2, regardless of how far apart they're separated. Okay? So this is a hallmark of what's called deconfinement, and the toric code is in fact one solvable point within an entire topologically ordered phase. This is a phase diagram of a Z2 lattice gauge theory with matter. And this is a very, very old problem which was studied in condensed matter in the 1970s. Okay? So you can get an entire phase with these deconfined charges and vortices, and the toric code is actually a solvable model within this broader phase. Okay? And the reason that deconfinement is associated with topological order is, I want these topologically degenerate ground states. Okay? So you think of this electric flux line as having these two endpoints, okay? But it's completely tensionless. And when those wind around the entire torus, that's what you think of as a logical error. But in condensed matter terms, it's the floppiness of those strings, which you can take it around the torus, bring it back, annihilate those charges, and then you're back to being in the ground space manifold. Okay, so you really need the strings themselves to not cost any energy, because if they did and you were trying to separate this out, you wouldn't get this topological degeneracy. Okay, so I have floppy electric strings, I have floppy magnetic strings. When I take them all around the non-contractible holes, I get these degenerate ground states. And really, this is a lattice version of, this is a gauge theory. You have charges and vortices, and you have electric fluxes associated with the charges. You have magnetic fluxes associated with the vortices. This is a Z2 lattice gauge theory. It's like a discrete version of something like a U1 gauge theory, which is familiar from electromagnetism. And this topological order with deconfined charges and vortices, it really extends into an entire phase of matter. The hallmark of topological order is stability. You can start with some topologically ordered point. You can perturb it in various ways. This extends into an entire phase of matter. And in fact, formally, we've known about this phase diagram again since the 1970s. Various features about proving the stability of this phase were mathematically formulated in 2010. And in fact, the conditions that were needed to prove the stability are precisely conditions of local indistinguishability, because the idea is to get from one ground state to another, you need to act with some very, very high weight operator. And that preserves some ground state degeneracy and preserves a gap for you. And these local indistinguishability conditions are actually very closely related to the Nil-Laflamme conditions of error correction. Okay, we expect this code space is stable because of local indistinguishability, and it's that same kind of local indistinguishability which also gives the topologically ordered system stability as a phase of matter. Okay, so this is the summary of what we've discussed. The repetition code is associated with the rising Hamiltonian. The toric code is associated with the toric code Hamiltonian. Code words are ground states. You have logical bits, logical qubits. And the symmetry operators of the model are your logical X and Z operators. And in one case, you have spontaneous symmetry breaking order. In the other case, we have topological order. Okay, let me stop there.
Okay, great. So we are on break until 2:45. We'll extend it just by 5 minutes.